Hey guys, my name is Kevin Lin, and today we're going to cover some problem-solving methods for algorithms. Well, the truth is, we're only going to cover some problem-solving methods for algorithms. There's a ton of different methods out there, as well as a ton of different algorithms out there. So the goal for today is we're going to cover three separate problem-solving methods for algorithms. Basically, the first thing that we're going to cover is multiple pointers in the VOD, so this doesn't concern you guys that are actually at this event, but in the VOD, basically, we're going to divide this into a three-part series. So let's hop into multiple pointers. So multiple pointers is just a way of creating basically a bunch of variables that keep track of different points in an array. These usually are just integers, an array or string, or even a linked list, but these are usually just integers or other data types that basically point to different points in time. And the benefit of this is it saves us from having to loop multiple times, and it usually gives us a more time efficient solution. So here's an example of using multiple pointers, right? So let's say we want to combine two sorted arrays. Well, the thing that we could do is we can create a pointer for our first array and a pointer for our second array. We'll call these pointer 1 and pointer 2 corresponding to their array names, right? And basically what we want to do here is since we have these two pointers pointing at different values in two different arrays, we have track of both of the arrays at the same time, right? So in our first iteration, what we want to do is we instantiate two pointers, pointer 1, pointer 2. They're both set to 0 because they're pointing at the 0 indexed item in their corresponding arrays. And then we calculate the values for each of these pointers or each of these pointers corresponding to the array. So array 1 pointer 1 basically points at 1. We're going to call that value 1. Array 2 pointer 2 points at the value 2, which we'll call value 2. So the first thing that we're going to do to basically create this combined array is we're going to compare value 1 and value 2. And then basically if value 1 is less than value 2, we're going to push value 1 in. So we're going to push the lesser of the two into our combined array. In this case, value 1 is less than value 2. So we're going to push value 1 in, and then we're going to move our pointer over because we've used value 1, right? So first we're going to push value 1 in, and then afterwards, after it's been pushed, after the value's been used, we're going to move our pointer over so we can't use this value 1 over again. Okay? Now in our second iteration, our pointer 1 is now at the index 1, our pointer 2 is now in the index 2. And we're basically just going to repeat that process where we compare the values at pointer 1 and the value at pointer 2. In this case, we're comparing 2 and 2, and basically they're equal, and it doesn't really matter in a sorted array whether we push this 2 or this 2 in. So we have to make a decision of whether we want to push array 1 in, array 1's value in, or array 2 values in. In this case, I'm just going to push pointer 1's value in. And if we use pointer 2's value, we're going to move pointer 1. If we use pointer 1's value, we're going to move pointer 1 over as well. So we're going to push 2 in, and then we're going to move pointer 1 over. Now moving on to our third array, our third iteration, we now have 3 and 2, and we're basically just going to do the same thing. We're going to use the 2 here since it's less than 3, and then we're going to move pointer 2 over. And we're just going to continue this process until we hit the end. Now notice one thing that happens here. Our pointer 1 actually exits our array 1, right? So there's no more possible values for our pointer 1. So what happens here is we can't do that comparison step that we had in the last piece of code, right? Because now nothing exists for pointer 1 to compare to. So basically we could have a conditional in our code that'll basically say if pointer 1 is outside of array 1, or if there's no more values in array 1, if that makes sense, then basically we just want to push the values from the second array, or vice versa in the case where pointer 2 is at the end of array 2, but we saw values in array 1, then we just want to push values from array 1. And then basically we're going to just repeat the process, but only for pointer 2 at this point. So we're going to push 3, move the pointer over, and then push another 3 and move the pointer over again. And now since both our pointers are outside of both our arrays, right? Basically we have no more values to traverse, so we could just return our combined array. So here's where we would stop our looping. So here's the multiple pointers in code, and you guys can really start to see the advantages of using multiple pointers as you walk through this function body, right? So one, our solution was O of n. We've only visited every single item one time. Two, we didn't have to really mutate either array one or array two or combine them in any way to basically tackle this problem. And three, basically, we're given two sorted arrays and we get to utilize the full potential of having two sorted arrays, right? Because the other way of doing this, which would not have been as efficient, would be to combine these two arrays, basically add them together. So we'd have 1, 2, 3, 2, 3, 3, and then basically sort it after. And that would be n log n time, which wouldn't let us take advantage of the fact that it's sorted. That gives us the opportunity to make it O of n time. Right. So here's our conditional that basically checks if pointer 2 is empty or array 2 is empty, or we finished all the items in array 2. And here's the code that basically just compares. And we're just basically pushing into our merged array and moving the pointers as see fit, right? So again, the advantages of using multiple pointers is it basically lets us point at multiple space points in time. The second advantage is it reduces time efficiency, it reduces the number of loops that we need to use, or it increases time efficiency, and it reduces the number of loops that we need, right? And it makes our code really a lot cleaner when we have track of multiple things in time. And also, since we can control basically where our pointers are, right, at each time we're moving pointers conditionally, it makes it easier for us to come up with creative solutions, or it gives us more control of the problem. All right, so does anyone have any questions for that? Okay, good. Let's move on. So, so basically, I want you guys to start practicing directly with multiple pointers. But before we do that, if you guys aren't set up yet, I know Johnny sent out a message telling you guys to set everything up. But if you aren't set up yet, or if you're watching the VOD, go to this link over here, this GitHub link over here, and clone that repo above. And make sure you clone the repo because if you fork it, you'll lose the remote to my repo, and then basically you won't be able to pull updates. And then basically when you have that on your local machine, make sure you install all the packages with npm install, and then do npm run test, and then write all your solutions in the file called test.js. And then when you're ready, when you hit save, if you did npm run test, it should load the test specs and basically check your answer for you. Okay, so I'm going to introduce the multiple pointers problem here. So the multiple pointers problem I want you guys to approach is called threesome. Basically, I want you guys to write a function called threesome that will take a sorted array of integers and a target number, and it'll return all the triplets that add up to that target. For example, if I gave you this array 0, 1, 2, 3, 4, 5, 6, and I gave you the target number of 6, I want you to return 0, 1, 5, 0, 2, 4, and 1, 2, 3, because each of these triplets add up to 6, okay? And notice that there's only unique triplets here. There's no duplicates, so there's no 0, 5, 1, for example, because that would be a duplicate of 0, 1, 5, technically. Now, here's some extra challenges. The naive solution will give you O of n cubed, but there is a better solution that uses multiple pointers, and that will make the solution O of n squared. And then think about what if the array wasn't sorted? Does that change the problem in any way? And also, and before you guys start, I want to give you guys a few hints if you guys need it. If not, feel free to pause this video if you're watching the VOD. If you're in here in person, I'm just gonna show the hints. They're not made to help you guys out that much, but basically put you in the right direction. So basically, if we're collecting triplets and we want to use pointers, how many pointers should we use, right? I'm not going to take any answers, so I know some of you guys want to tell me, but I'm not going to take any answers for the sake of you guys thinking this out on your own. Next is notice that we specifically say we're given a sorted array. When an interviewer tells you that when an interview gives you some piece of information, you have to think about why did they give me this information? Why is it important to my final solution, right? So think about that as well. Also, the next thing is whiteboard it out, right? So in my first example, notice how I basically walked through the problem without any code first, right? This is really important to do, especially when you're whiteboarding, because it helps both you and the interviewer, right? In the sense that you can visualize the solution and the interviewer will know where your mind's at. And then afterwards, writing the code will basically be really easy. Just because you have a good sense of how the problem should work or how the solution should work. Like, okay, and then finally, try a really small array. Try like maybe just four numbers, so maybe like 0, 1, 2, 3. That would be a good input, especially if you're whiteboarding it out because it saves you a lot of from writing a lot of iterations. All right, and now I'm gonna let you guys work on it. I'm gonna give you guys 30 to 45 minutes to work on it. Do your best. If you guys get stuck, I will be walking around. So just raise your hand. I'll walk around and check in with you guys. Also, you guys feel free to pair program if you want to. That, but it isn't necessary to do so. I will walk around and basically give you hints. Okay. If you guys are watching the VOD, there will be a cut here. So just wanted to point that out as well. Okay. All right, guys, we're back. Thank you again to Alan for basically walking through that whiteboarding problem. So again, like if you guys don't feel confident whiteboarding, like feel free to if you get a solution, feel free to walk up and just like whiteboard it out because the goal of this whole meeting is basically just to get you guys comfortable with doing these whiteboarding interviews. So like even if you're not comfortable doing the problem, feel free to like walk up and just whiteboard it out, just like Alan just did. So again, like shout out to Alan. But yeah, let's continue. I'm going to explain the solution again for the people watching the VOD. So here's a walkthrough of three sum with multiple pointers. Basically, what we want to do is we want to create a for loop. You guys will see in the code later, but we have three pointers here. So we have a pointer pointing at 0, one at 1. So basically the first item in the array, the second item in the array, and then finally a pointer at the last item in the array. This item in the array will continue to increment by 1, and we're going to continuously play with these two pointers here to basically calculate a target sum, right? So here we're going to take the value or the summation of whatever these three pointers are pointing at and basically return and compare that against our target and then move these pointers as we see fit, right? Basically to compare it to the sum. So here if we add 0 plus 1 plus 4, we get a sum of 5. If we compare 5 to our target, 5 is actually less than 6, right? Now, the fact that this is a sorted array actually helps us a lot. Since it's a sorted array, we know that the number to any number to the right of 1 will either be equal to 1 or larger than 1, right? And then we also know any number to the left of 4 or will be less than or equal to 4, right? So in this case, we know that since we know that the number next to 1 to the right of 1 will be greater or equal to 1, we can say since our sum is equal to 5, right? Let's move this pointer over by 1 and see if our new sum afterwards is equal to 6, right? And basically this is just a reiteration of this. Since our sum is less than 5, we're going to increment pointer 2, or basically this pointer over here. So after we increment our pointer, we check again, and we're going to say 0 plus 2 plus 4, and that is equal to 6. Since it's equal to 6, right, we're going to push 0, 2, and 4 into our solution array, since it's equal to our solution. Now, it's equal to our target. Now, after we push, we also have to do one more step. I know a lot of you guys were having trouble doing this step, but basically you don't want to just push. You also want to increment both pointers in. The reason we want to do this is because basically if you don't increment or decrement the pointers in any way, in the case where you push, basically the while loop will run forever, right? You're going to keep hitting this statement here, and you're just going to keep pushing 0, 2, 3, 4 into your solution. And then these pointers will basically never overlap, so your loop will never end, right? So basically, we want to in the scenario where we want to increment both this pointer and we want to decrement this pointer. The reason being that since we hit our target 6, right? Basically, we can't only move this pointer to the right or to the right because basically any number to the right of 2 will be larger than 2, right? So since we're at our target, if we only move our left pointer to the right, we're going to have a number that's always going to be larger than our target. And if we only move vice versa, also if we in the other case, if we only move our rightmost pointer to the left, right? Basically, since we're at our target, we'll always have a number less than our target because of the way that the array is sorted, right? So in this case where we push into our array, we want to move both our left and right pointers in. And basically what happens here is this gives us the opportunity of bumping into a new combination that can also equal our target. Right? So in this case, since we push both in, right, we move both inwards, right? They're overlapping now, and we can't really use this triplet, even though we're at 0, 3, 3, and that's equal to 6. We can't really use this sum because both of the pointers are on top of each other, right? So we're just going to break out of this because this is technically not a triplet. We're reusing a number here. And then notice here in our next iteration, so we're going to have two loops here, right? Notice in our next iteration, we're going to move this pointer inward to 1. And now this pointer is at 1, and basically these two pointers will always be, this last pointer will always be at the last item of the array. This pointer will always be 1 to the right of the first pointer, right? And basically we're just going to run the steps again. So we're going to do 1 plus 2 plus 4. That's equal to 7. 7 is too big, right? So we're going to say, okay, since 7 is too big and our array is sorted, we're going to have to move our right pointer to the left because the numbers left of 4 are always less than 4, right? So if we move our right pointer to the left, we get 1, 2, 3. And 1, 2, 3 is equal to 6. So we're going to push into our solution array. And then finally, remember again from the previous solution, in the case where we push, we want to move both of the pointers in and over, right? We want to move both of the pointers inward. So this will go to the left, this will go to the right. In that case, right, since our pointers cross, right, we're going to basically just break out of that and move this one pointer over. So now we have 2, 3, and 4. 2, 3, and 4 is equal to 9, and that's way too big. So we're going to try moving our pointer 3, or our rightmost pointer, over to the left to reduce our current sum. If we do so, we get a current sum of 8, but now we have this overlap here, so basically we want to break out of the loop. Also notice that we don't have to increment this outer loop anymore because we are counting for these two pointers will at least always be one number ahead of this pointer. So once this pointer hits 2 items from the left of the end, we already iterated through the entire array basically. We've already reached every possible triplet set, right? Because these pointers will always point at different values to the left of that pointer. Okay, and now let's walk through the code if this makes sense to everyone. Okay, let's move on and walk through the code. Okay, so we instantiate the 3sum function, and it takes an array and a target, right? And then we have const results, which is equal to an empty array. First, we're going to sort the array. So this is the case where we don't have a sorted array to begin with. The reason why we could sort the array and not like really worry about the cost of doing this is because basically this cost is larger than sorting. So sorting is n log n usually, and since it's n log n, right, n log n is actually faster than n squared, which will be this nested loop here. So the n squared for a really large input will actually outweigh this n log n operation here, right? And we also gain the advantage of using a sorted array. Because if the array wasn't sorted, we wouldn't be able to move these pointers in like this. We wouldn't be able to set up our pointers like this, right? Because now, if it's not sorted, moving our leftmost pointer to the right, our rightmost pointer to the left, basically won't guarantee that our target will decrease if it's not sorted, right? So having it sorted is advantageous for that reason, and it's still going to keep our solution O of n squared at worst. Okay, so basically inside our for loop, we want to declare our left and right inside our for loop, right? Basically, we want our left and right to be entirely based on the position of this first pointer here, right? And we can do that by basically changing it by declaring it inside our for loop. And then in this, we're basically saying while left is less than right. So this ensures that our left pointer or pointer 2 and 3 here, that these two pointers never overlap. Or we basically can't have a solution where we're using one number twice because these pointers will never overlap. Also notice that we did array.length minus 2 because we have these two pointers that are always to the left of the first pointer, right? So we don't have to keep track of the two other numbers with this I variable just because we already have these two variables over here. Inside the while loop, we want to calculate the sum every time we iterate. So we want the sum of the left plus I plus right. And then we're basically saying if the sum is equal to the target, basically just push that triplet into our results array, and then increment both pointers inward. So left will increment, right will decrement. Otherwise, if the sum is less than the target, then we're going to move our left pointer over to the right, which will essentially increase our sum. Otherwise, our value is less than or greater than our sum. We're going to move our right pointer to the left, which will decrement our sum or decrease our sum. And then we're just returning the final results array. Okay, does anyone have any questions? Okay, awesome. Let's move on. Okay, so I wanted to show that multiple pointers aren't explicitly restricted to strings and arrays. Now, like it's often thought that like I know like as you guys are thinking of this method and you're like really trying to absorb the whole idea of multiple pointers, the use cases that come to mind are you generally always going to be strings and arrays. Um, just because it's easy to think of it for strings to think of it in the sense for strings and arrays, but I want to show that they can also be used for other data structures. So even though we're not covering linked lists today, I want to show that it's possible for linked lists. Um, and I want you guys to remember that it's possible for linked lists because it's just a method of keeping track of multiple things at one point in time, right? So it's usable for a lot of different data structures and data types. Okay, so I'm going to introduce a problem here. So given a node in a linked list, can you tell if it has a cycle? So basically a cycle exists if a linked list has a node that points to another node within that linked list, right? So basically what ends up happening is the linked list will loop, right? So if we iterate through this, we'll go 1, 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4, right? Basically, this has a cycle. So this will return true. It'll basically loop infinitely. This is just another case, right? So this is a regular linked list where it basically doesn't have a loop. So this will eventually go to null or no value because 3 doesn't point to anything. So this will return false and this will return true. Okay, so let's walk through this problem. Actually, for you guys that are watching the VOD, feel free to approach this problem on your own. I will walk through it for this class because we're a little bit behind on time and I want to at least cover shifting frames today. So we're going to walk through this right now. So basically, we have the circular linked list and just visualizing it out, right? We have this one pointer. This pointer points to the head or the given node, right? This could be any node within the list, right? Now we're thinking about multiple pointers, right? So the first thing that comes to mind is, can we do something if we have another pointer? And this pointer, I'll basically just put it next of pointer 1. So basically it's just pointing at a different node or the node right after 1, which is just the given node dot next. So if we play around, if we have multiple pointers, right, given the nature that we're doing multiple pointer problems, is there anything that we could use with multiple pointers that can tell us if there's a cycle? Well, let's look at it, right? So if we move both of these pointers around, it doesn't really do anything. In fact, they'll just loop infinitely again, right? So that doesn't really do anything. So instead, let's think of an analogy here, right? How do we tell if there's a loop in a real life setting, right? So think of a racetrack. A racetrack is basically a cycle. Drivers basically have to complete a certain number of laps to win the race, right? So in this case, it makes sense, right? So you could think of this as a cycle here, right? Where we have two drivers here. We have the blue driver and we have the red driver, right? Now think about a case where these two that might help us lead to the answer, right? What's special about this scenario that helps us? And I kind of give you a hint in the picture. Does anyone want to tell me what it is? Yes, absolutely. That's perfect, right? So basically, the drivers can overlap or they can be in the same place at the same position because we're in a circle, because we're in a loop, right? So basically, if we have 2 points along a circle, we can basically interact at some point, or inside of loop in this case, but we can interact at some point, or we can overlap the 2 points at some point because they're not following the same position, right? Now, what do we need? What criteria do we need for this to happen, right? We need one car to be faster than the other. One has to grow at a faster rate than the other, right? So in this case, notice how the blue car was in the back, the red car was a little bit ahead, but now the blue car caught up because the blue car is moving a lot faster, right? So now let's see how we can apply this to our problem, right? So let's try doing this, but now let's start our pointers at the same point in space. But this time we're going to move our red pointer only one, and our blue pointer, we're going to continue to move it too, right? We're going to move it now faster, so we're going to move our blue pointer by two nodes instead of one, right? So in this case, first case, our red pointer points at 2, our blue pointer points at 4 because it's traveling by 2. Our next iteration, they're on top of each other, right? So now that they're on top of each other, going back to our track solution, if they have if there's a scenario where they could be on top of each other, granted one traveling faster than the other, right? Then we can confidently say that there's a cycle, right? So now the next thing to do is just to make sure that this works on a non-circular or circular linked list or a linked list that doesn't have a cycle, right? So in this case, we're saying if pointer 2 ever hits null or outside of our linked list, we should return false. So in this case, we have both our pointers pointing at 1 and 2. So this is a given node and this is the given node's dot next, right? So in this case, our pointer 2 hits null. So we hit false, right? So it works for our normal case. All right, that's great. And this is just the code for that. So let's walk through this line by line. So we're saying if the node is null, so this is just an edge case if they basically don't give us a null, then, or if the null node.next is null, so basically if we can't point at the next node here, then we'll just return false, right? Also, that could just be a scenario where the head doesn't have a next anyways, so it definitely doesn't have a cycle, so we would just return false in that case. So we're going to create a variable called current node, and that's just going to point at the current node because we want to be able to reassign this variable to keep track of the next nodes, right? And we're going to do the same thing with our end node, but our end node is going to be the node directly next to our first node. And basically we're going to say while our current node does not equal end node. So this basically saying while they don't overlap, right? Right? Then we want to run this code in here. So we're saying if end node is equal to null, so if our end node ever goes outside of our linked list, right, then basically we can return false because we know that there's an end that exists, right? And we also want to check endNode.next. We want to check if that has a null because we basically don't, if we did dot next of null, right? Basically what would happen is it would give us an error. It would just basically say null doesn't have a property of next. So that's why we have this line here, just to make sure that we don't have that error, right? And then basically if this doesn't get hit, we're basically saying current node equals current node.next. So we're moving our current node by 1 over, and then we're moving our end node 2 over, right? So our end node is growing by 2, our current node is growing by 1. And then finally, we're going to return true if our end node ever equals null, right? Or we're going to return true if our nodes ever overlap, right? Okay, and that's the end of this portion. I'm going to pull up the other slide for the other portion of this setup.